Hello everyone and welcome to tonight's Unit 3 revision. Now this is for everyone that is sitting the WJEC Unit 3 exam tomorrow. We're all very excited about it, undoubtedly. We're really clearly thrilled to finally have exams. Yeah, well, luckily for you guys, hopefully they'll be nice to you. Now just a reminder, what the WJEC have said to us already is that they are going to try and be nice to you. They're going to try and be fair, but you've probably heard what's happened in some of the other exams, and I'd just say that even if you've memorized the exam papers and the past papers, there might be a few surprises for you as you go through it. So please do make sure you've done the past papers as much as possible, because there are some weird things, and let's just get straight into it, is it? Because there's a lot to do tonight. So first things first, if you are doing any more revision tonight or tomorrow and you want some resources, I've put 3 sets of videos up on every topic for this unit already on my YouTube channel, on that playlist right there with the big blue arrow pointed at it. It's A-Level Computer Science, WJEC Unit 3. There are videos where I'm talking about what the learning is, going through past paper questions and going through workbook-based activities that I've made up to try and sort of cover the bits of the specification that haven't had questions asked about them. Please do check the past paper questions. Some of the ways they ask questions are really weird and are really not anything at all like what you'd expect if you were going purely on the learning, especially things like data structures and stuff like that. So please do look at those past paper questions. Now, let's have a quick look at what they've said about this year. This is the most recent, most up-to-date summary of what would have changed for your exam. So the 2 units that they've left out is Unit 6, Systems Design, and Unit 8, Program Construction. Now, what that probably means is the exam paper that they'd already written didn't have those 2 topics in it. Well, that's great for us because that's 2 less things to learn about. However, not quite that great because there's still these 6 topics, of which the first 3 are huge. 4, 5, and 9, not so much. But the first 3 are absolutely huge and probably will be where the majority of your questions are coming from. Now, as long as you've got some mastery over these sections, you should be okay. But please do have a look over these past paper questions. Like I said, on my website, on my YouTube channel, there are videos where I go through the past paper questions and talk through the mark schemes. Please have a quick fast forward through those if that's the only thing that you do. Yes, sorry, software engineering is on there, but I have clearly left it out of my to-do list on here, but the slides are in there, so don't panic. Software engineering is there. I had a bit of a panic then. Software engineering is a really small chapter. It's like 2 or 3 things. It's basically nothing. Okay, let's get started because I've got a shocking 500 slides to get through tonight. A lot of it is animation, and most of this is just stuff that I've already talked to most of you about, but it's good revision resources. So let's get started with data structures. First and foremost, arrays. Key things to remember about arrays, because if you've learned Python, if you've learned other programming languages, you probably think you've used arrays, but haven't. A true array is the same data type. Everything in it is the same data type. It needs to be static in that it's a fixed size. It can't grow or shrink. Now, it can be multidimensional, and it is what we call a random access data structure. And what that means is if I pick any cell randomly, I can access it in the same amount of time as any other. So, quick reminder, 1D arrays on the left, everything's 0 index, so it starts from 0. Notice they're all the same type. One-dimensional arrays are less useful most of the time. They're handy to keep a list of something in, but then they're just a list of individual items. If I were to access maths, I'd need to access it with the square bracket and the row number. So I'd access that with subjects and 1. So it's the array name and the row number that's really the important bit about that. Now, a 2D array is great. I've got rows and columns. If I wanted to access the cell with Mrs. James in it, I'd have 2, 1. Notice it's the row number first. It is not like maths. It is not like geography. And the reason for that is really that this isn't actually what this data structure looks like at all. This data structure is actually this, where in each row, we've got another one of these. So it's arrays within arrays. So we've got a load, a massive amount, almost an infinite amount of dimensions we can go to. Key examples here is that a 1D array would be a list of individual things, and a 2D array would be something like a timetable. So what about 3D arrays then? Because at A2, we need to know about 3D arrays. Well, it might be something like this. It's the timetable through different days of the week. Now, if I'm accessing that, I'm going to have in the first square bracket, I'm going to have the table index. So zero index as well. So this is table index 2. Then I'm going to have the row once again, and then the column. Now, of course, we can go up to an infinite amount of dimensions, really, as long as the computer can support it. But you only have to know up to 3 in your exam. I doubt that they would ask you a question that involved you writing code for 3-dimensional arrays, because it gets very complicated very fast, and there's a lot of code needed to understand that. I've never seen a question with 3D array code, but I have seen questions that ask about 3D arrays in a written form. Okay, next, a stack. A stack is a last in, first out data structure. So the last thing in is the first thing that pops out. It looks like literally a stack of things. It's computationally simple, which means it's easy to think about, it's easy to program, and it's dynamic. It can change size. So this is a stack. This is probably our list of things that we need to do. If I want to add a new thing, it goes on the top and the pointer moves to point to the top. If I want to take something out, I have to take it out from the top and the pointer moves to the new item. Notice in that example, revision still stays at the bottom, despite the fact it was the first thing that went in the list. That is one of the problems with stacks. Queues, first in, first out. This is literally a queue of items like you get in a supermarket. You must keep track of the front and back of the queue, and you do that with pointers. And once again, it is dynamic. I'm just going to pick up on this because I'll try my best to get it over by 9 so you can go and watch Love Island, but just record it. I mean, you got an exam tomorrow. Watch it back. I know, before the English exam or something. It's got to be more relevant to that. Anyway, cues. Front and back with a pointer to both. If I add a new item, it goes in at the back. He says confidently, as none of my animation's working. There we go. It goes in at the back, and notice the pointer moves to point to that. If I want to take something out of the queue, I take it from the front, and the front pointer moves to point now to the first item in the list. Queues are brilliant because they allow us to take things out fairly and get to every task eventually. Linked lists are even better because they contain data and a pointer to the next item. Now, this is a common question. This is normally what they like to ask you about because they are nice to ask questions about. The only problem with them is they're not a static array in memory. They're not just a chunk of data. You must traverse them. You must move from box to box to box to find them. If items are added or removed, we need to create or change the pointers, but that doesn't mean it's dynamic. So here's a linked list. So in this linked list, I've got cooking, then homework, then revision. On the bottom right, you'll see that's what it might look like in memory. Item 0 could be homework. Item 1 could be cooking. Item 2 could be revisions. They're not in the same order, but notice the pointers. Our first item is cooking. That points to 0 next. So we follow that to 0 and we go to homework, which points to 2, which is revision, which is null. Now, there's a common question at this point that most people ask. It is, how does the computer know which is the first one? There is also a pointer usually to identify which is the first item in the list. However, it is not mentioned in your specification at all that you need to identify the first one. You can sort of assume that the one that isn't pointed to is the first item in the list if you can help it. Do we need to know the pseudocode for it? I mean, the reality is they could ask you pseudocode on anything. But don't forget, if they ask you to write code, you can write it in any programming language you want. It doesn't need to be pseudocode. If you're interested in the questions for linked list, do go to my YouTube channel and find the data structures past paper questions section. There's loads of linked list questions in there. I haven't got time tonight to go through the past papers as well. I'm sorry. So a new item comes in and I want it to go between cooking and homework. Or what do I need to do? I need to change the pointer from cooking to point to that. And please notice what's happening in the array on the right-hand side. The pointer from cooking, which is currently going to 0, is now going to 3. And then I need to take a pointer from gaming and put it into homework. In the array then, I've added a pointer to 0. If I want to delete an item, then basically I need to move that pointer from gaming to pointer revision. But notice I haven't deleted cooking from the array. It's still in there. It's still in the memory structure. That's the beauty of a linked list. I don't actually need to delete things when I remove them. I just remove the pointers. So I can't actually traverse to get to that area. And this is normally what the questions look like for linked lists. It would be things like, show me how a linked list looks. Show me how the data structure works for this illustration. Show me how you'd add something. Show me how you'd remove something. They also very much like this question. Trees. Binary trees are built of nodes and branches. Okay, each node has a maximum of 2 branches, one to the left and one to the right. Now they're brilliant because they're extremely dynamic and they are sorted as part of the creation process. So you don't have to do sorting on them. But there are many different ways of traversing the trees, and you need to know all of them and be able to perform all of them in the exam. That's harder than it sounds. So here is a evenly distributed binary tree. That's because every node has 2 branches coming off it. It doesn't need to look like this, but this is commonly what they might give you. Now, if we're going to insert data, we start at the root node, which is John in this case. If the data is greater than, it goes to the right, and if it's less than, it goes to the left. And we keep doing that until we find an empty branch for us to put it on. And in terms of greater than, we're talking alphabetical order. I know my class, for some reason, don't remember the alphabet. Please write the alphabet from A to Z across the top of your exam paper, the top of your question paper, so you don't make silly mistakes. It is a very quick job to write the alphabet, so you're not having to do it in your head every time you're comparing values. So if I'm inserting Lorna, I'm going to start at John and I'm going to say, right, is L come before or after J? Well, it comes after, so I'm going down to the right. Now there's already a node there, so I need to do the same thing again. Is L before or after N? Well, it's before, so it goes down to the left. There's a node there, so I need to do the same question again. Is L before or after K? It's after, so it goes to the right. There's an empty space, so the node can go in. Paolo, no, you don't need to know the pseudocode for the alphabet. It's going to go well tomorrow. I can see it. I can see it from the sort of questions. Right, sorry, to delete data. There's a couple of rules here. If the node has no child branches, there's nothing coming off it, we can just get rid of it. If there's one child branch, then we just take the link and we pop it to the parent. So we just put that link above it. The worst case scenario is if there are 2 child branches coming off it. And in that case, we need to update the root. Let's show you. If I'm getting rid of Alex, then it's just this. He's gone, sorted, no problem. There was nothing coming off it. If I want to get rid of Barbara, we've got 1 child node. There's something underneath it. But all we need to do is get rid of Barbara and link the child to the parent. Boom, Barbara's gone. Now the difficult ones are going to be Norma, because once we've got rid of Norma, we need to take the smallest node, in other words, the leftmost one, and pull that up to replace where Norma was in the tree. It still makes sense then, and we can go from there. I'm slightly concerned that people are talking to the Restream bot. I hope you know the Restream bot is just the thing that is helping you communicate between Twitch and YouTube, but fair enough. Anyway, pre-order traversal. Right, this is the most straightforward one. Root node. Record the result as you visit each node of the leftmost until there are no more children. Okay, so what this means is John, because I visited John, I go left first. Barbara, write it down because I visited Barbara. Left first. Alex, right, Alex down. Okay, no more left to go. So I go back up and to the right. Bush, Karis. Okay, no more nodes to visit. So I go back up. No more nodes to visit. I go back up. I'm going to the right. Okay, I visited Norma. Norma, you can go on the list. I've got a left and a right. If I have an option, I always go left. I get Kieran. And then finally, last one, Xavier. Boom, done. Pre-order traversal. The easiest, the most straightforward type of traversal. You need to know the names of these things as well, by the way, because they will just ask you, please do pre-order traversal. They're not going to give you much detail on it. In order traversal. Left subtree, then the root node, then the right subtree. So we're not writing them down as we visit them. We're writing them down as we get to the bottommost node of that type. So for instance, start with John. There's a left and a right, so we go left. Barbara, there's a left and a right, so we go left. Okay, there's nothing else below it. I can write Alex down. Okay, back up. I've hit the node. I've hit Barbara. Write her down. But I can go right. Down we go. Karis goes in there. Boom, because there's nothing else left. Back up. I've visited John. Boop. John goes in. To the right. Norma. Visited Norma. But I have to go left first. Down to Kieran. Nothing else. Kieran. Norma. Xavier. Boom. Done. That one's a bit weird. Post-order traversal is a little bit better. Root node first. Then we go left until there are no more children, then right. So, in this case, going all the way down to the left. Haven't written anything down yet. I've got to the left. Boom. Alex. Go back up. Go right. Karis. Notice I didn't write Barbara down. Just because I'm visiting doesn't mean I'm writing anything down. When Barbara's the bottom node and I can't go down from her anymore, then she gets written. Okay, nothing for John because I can go right. Nothing for Norma because I can go left and right, but I'm going to go left first. Kieran goes up there because he's an end node. Xavier goes up there because he's an end node. Then Norma, then John. Okay, again, just need to go and learn these things. It is not the most fun thing in the world because they are very, very similar and they're very, very easy to forget which one's which. But go and practice them. Go rewatch the videos. They're all there. The animation's beautiful, if I do say so myself. Hashing algorithms. Okay, so hashing. The point of hashing is that we want to give some piece of data a numerical value. What does that mean? That means in some way we convert text or an image to a number. And the reason might be usually because what we want to do is we want to put that into an array. Now, in this example, it's no faster to do this than it is just to stick data in and search it. You've got to imagine that this array is billions of cells big. Okay, otherwise it doesn't make any sense. But this is what we might do. A simple hash algorithm might be like this. If I want to take the word test and put it into the hash table, I'm going to take each letter and give it a numerical value. A is 1, B is 2, so on, so on, and so on. Then I'm going to add those values up. All great. Problem is, I've only got 16 rows in my array. So I'm going to have to mod 16 that. That's give the remainder of 16. That gives us 0. So it's going in the first box. That's a very, very simple hashing algorithm. Okay, let's try it again. Hi. So hi, H and I, split them up. H is 8, I is 9, add them together, 17. 17 is bigger than the amount of rows in the array. So we'll mod that 16. That gives us a remainder of 1. Whoosh, straight in there it goes. Okay, so what happens when we're adding something like P? P is 16. 16 mod 16 is 0. Oh no, 16 needs to go in position 0, but there's something there. This is where we find a collision. And in the most case, in a collision, what happens is we just look for the next space after it. So I can't fit it in there. Can't fit it in there, but I can fit it in here. And this is where hash algorithms sort of fall apart a little bit, because you do still need to do an element of searching. Okay, let's see how we find something then. Let's see if I can find high. Well, to find high, I compute the hash value and I look in that box. If it's there, happy days. What about finding Mr. M? Well, let's compute it. Mr. M is not in the hash table. How do we know? We worked out the numbers, we worked out the hash value, and we looked in that cell. There's nothing there. Hash tables, what we are trying to do is reduce collisions and evenly distribute the data. They tend to ask more complicated questions about this in Unit 4. So they're unlikely to ask questions about this in Unit 3, but they still could. Okay, one down. That's half the time almost. Let's get going. Logical operations. Okay, so key thing for this one, logical operations, normalization. You need to know the AS stuff. For you guys, this is a major problem because you didn't have AS exams. You didn't have to go and force this stuff into your brain in quite the same level that every other year group has had. So here's my suggestion for you. I put my arrow in the wrong place, but this playlist here, logical operations and Boolean simplification, does all the logical operation stuff and the simplification stuff right up to AS level. So just before where you need to be. If you need a recap on any of the simplification stuff, please go and ask that. Quick question here. Could they ask us to write a hash algorithm? They could. You need to know about it. But the most common type of question they ask is that they give you the maths of a hash algorithm and ask you to work out a few values. Then they'll ask you why it's no good or what could be better and all that sort of stuff. So if you need a recap of simplification, please go grab that video series, about an hour long, put it on 2x speed, watch it in half and bash your way through it. AS content with these gates, a NOT gate, an AND gate, an OR gate, or an XOR gate. They all did things to inputs zeros and ones. Okay, so a NOT gate would give you the opposite. A 0 would become a 1 would become a 0. An AND gate, you needed both of the inputs to be on to get an on out of it. An OR, either or both of the inputs had to be on to get a 1 out of it. An XOR was only one of the inputs had to be on. A2, you've got some more gates. A NAND gate. Well, NAND is short for not AND. So what that means is the output is going to be a 1 as long as both inputs are a 0. So it's this truth table here. Look at the symbol they use. It's an upward pointing arrow. Thanks, guys. That's very helpful. The upward pointing arrow or the not AND gate, both of them have to be off to get a 1. And if there's anything else, if both inputs are true, we get a 0. So it is literally the opposite of an AND gate. Just imagine that it's an AND gate with a not symbol before it. That's all we need. Do we need to know the symbols? It's not entirely clear from the specification whether you need to know the symbols or not. I've never seen them use the actual illustrated symbols, but they do sometimes use these, the up arrow symbology as well as NAND. You wouldn't need to normalize a NAND gate, though. There's no normalization process for it. Okay, NOR, again, not OR. It's an OR gate with a not in front of it. As long as both inputs are not false, we're going to get a 1 out of it. Notice the symbol is a down arrow. So if they're both off, we're getting a 1. But if any of them are on, we get a 0. It's literally the opposite of an OR gate. Now, again, here's a question. Could they use the symbols? They could, but they probably won't. But I don't write the papers. I'm just giving you my best guess, all right? They haven't ever done it so far. Okay, right. Here's an interesting one. Applying logical operations to data and what they're for, okay? A NAND gate, if you've got an input value and a key, let's see what that does. Remember, it's not AND. So the only time we get a 1 is if they're both 0. So the only time we get not AND is the opposite of an AND gate. An AND gate only gives you a 1 if they're both on. So if they're both on, in this case, it's off. Otherwise, it's a 1. Right. So 1, 0, 1, 1, 1, 1, 0, 0. Okay. That's what we're looking for when we're applying that. It's very, very straightforward. You can use these operators to do special things in the CPU. Okay. An XOR gate can clear a register completely. You can wipe it to zeros very, very quickly. If you've got a register with the input value 01001111 and you copy and paste it to be the key and you XOR it with itself, you get zeros. So one of the best uses for an XOR gate would be to wipe the registers out. Okay, questions about the arrows. The arrows are the WJEC specific symbols. So please do try and remember them if you can. I would write them out longhand. If you need to write them out, I would write out NAND or NOR. I wouldn't use the symbols myself because you want to make it 100% clear what it is, but they could use those things. Okay, AND gates for masking. What an AND gate can do is you can hide parts of a binary expression. So if, for instance, in this input, I only wanted the two most significant bits, I could use this key as an AND gate, and it would only copy down the values for the first two places. Wherever you've got a 1 here, you bring that down. This question, why not use an AND gate with all zeros as a key? You could do that as well. Yep, that's for the previous one. You could do that as well, but you'd need to load those zeros in. Having the same two input and key is quicker on a register level and like a CPU processing level. Encryption, use XOR. With XOR, you end up with a symmetric key. So I can put this input in with a key I've made up and get this result. And then I can do it the opposite way around. If I put the result into the key with an XOR, I get back to the input. So it's very good at doing encryption because I can go back to the original very, very quickly. Now my favorite, De Morgan's Law, or De Morgan's Law. This is why it's my favorite, because, you know, my initials. But it's just a very simple way of converting from a joined statement to separated statements. So not A and B is the same as not A or not B. Similarly, not A or B is the same as not A and not B. The top one is the most commonly used form of De Morgan's Law, because if you remember, the and sort of works like glue and the or sort of works like a separator. So what the top one does is sort of separates out the terms so you can more easily simplify the expression. Okay. So what we're doing is splitting and change the operator or merging and change the operator. The top one is the most commonly used form. And what they normally ask you to do with De Morgan's Law is they will say, oh, use De Morgan's Law on this expression, wink, wink. And when you apply De Morgan's Law to it, you'll see an expression that can be further simplified. And that's part of what the marks are for. So let's have a look at this one as an example. Not A and C, or not B and B, or not B and C. So the first thing we might do is factorize. Let's factorize out the and C. Okay, the moment I factorized out the and C, I'm left with C and, in brackets, not A or not B. And the moment you see not A or not B, you might go, De Morgan's Law, let's apply it to that bit in the brackets, because what I end up with is not A and B. Okay, what might you do with that then? Nothing. That's as far as it goes. It's a very silly example I've given you, I'm sorry, but just to show you how you could apply it to a situation. What they'll probably get you to do is actually do it the opposite way around. So you end up simplifying and removing bits from it. Okay, time is not our friend tonight. If we want to get you out and ready for Love Island, we're going to have to pick up the pace a little bit. 3, algorithms and programs. Right, so what's an algorithm? It's just the technical term for the instructions you're using to run a computer program. It is, since time immemorial, the way that computer scientists have made ourselves sound clever to other people. You can define an algorithm using a flowchart, using all those specific symbols there. We've got our terminators, start and end. We've got our rectangular process blocks, our decision diamond, our subroutine, our labels, and we've also got inputs and outputs, which are parallelograms. You also need to understand pseudocode, not necessarily to write it. Anytime they ask you to write pseudocode, you could write it in normal code, but you do still need to read it and understand it, but it is very, very straightforward. If you've learned Visual Basic, this is pretty much what pseudocode is. But the problem with pseudocode, and I've said this to my class a million times, pseudocode should be based on the language that you're writing in. If you write in Java, it should look like Java. If you're writing Python, it should look like Python. The way we do it for exams is absolutely ridiculous that there's a form of pseudocode that looks like Visual Basic that we have to learn. Ugh, makes me feel dirty just talking about it. Quick question. Yes, the shapes are necessary to know because you will be expected to draw or interpret, but they should be straightforward. The main things you need to remember are parallelograms are input and output. The diamond is a decision, so it's a question, and there'll be multiple parts going off it. You may need to interpret or fill out a chart from that. Okay, recursion is the biggie in A2. It's the thing they love. And you'll know they'll love it because they'll talk about how elegant our algorithms are. Well, yes, recursion is an elegant thing, but also recursion makes your code a nightmare. I can count on one hand the amount of times I've seen a recursive algorithm used in production code because the problem it has is quite significant, and we'll get onto it in a minute. But the idea is this: if you've ever watched that Mr. Meeseeks episode of Rick and Morty, it's basically that. It's an algorithm that calls itself until one of the versions of itself fixes the problem. And then, with a terminating condition, the rest of the recursions can disappear. Of course, if it can't solve the problem, it will keep calling itself until all the computer's resources are tied up in trying to solve this problem. So there are significant issues with recursive algorithms, despite the fact they look elegant. So what have we got here? We've got a factorial procedure. So what the factorial procedure says is if it's 1, then we return 1. Factorial 1 is 1. Fine, that's our terminating condition. But if it's not, we're going to return the value multiplied by the factorial of the value minus 1. Right, so what that means is if we start it with factorial 3, this is what happens. Okay, it goes into the if statement. Well, it's not that. We'll go to the else. So I'm going to return 3 times factorial 2. Oh, but I don't know what factorial 2 is. So let's do factorial 2. So the program calls factorial 2. Factorial 2 goes in and says, is the value 1? Nope. So we're returning this. So I'm going to return 2 times factorial 1. Do I know what factorial 1 is? No. Call it. Factorial 1, yes, the value is 1. So I'm going to return 1. So factorial 1 becomes 1. That pops up the stack. Factorial 1 now gets replaced with 1. That means I can now calculate factorial 2. 2 times 1 is 2. That pops back up. I can now calculate factorial 3. 3 times 2 is 6. There's my answer. Boom. Seems straightforward. Every time it calls itself, it needs the memory space and the processing power to do so. You can fill up your RAM with recursive algorithms quite quickly. The word you want to use if you're talking about it is elegant, because they love that. It's elegant because it uses divide and conquer to break it down into smaller and smaller subproblems until we work out the final answer. It's simple and compact, but it uses shed loads of memory. So you probably avoid it in the real world. Test data, right. Okay, one of the things they might ask you to do is work out test data for a program. You want valid data, data that should work, invalid data, data that shouldn't work, and extreme values. Now, extreme values are the hardest ones to understand. If you've got a range of options, for instance, you've said, okay, I'd like you to type in your age, and the age goes between 0 and 100. Extreme values are both ends, 0 and 100. They're the highest and the lowest acceptable value. We also need to make sure that it runs all code paths. It goes down every if, elif, and else that exists. And the way we do that is we perform dry runs. We work through the code line by line to show what's happening and show how it executes. And then we check we don't have logic errors. This is often a bit of a faff if you're asked it in an exam, because you might be given a subroutine like this, and you might be asked to dry run it. Well, what does that mean then? Well, normally what we'll look at is we'll look at the looping, the iterations. So first time through the loop, if you read the program, erroneous data, that would be invalid in my model. Okay, so invalid is just wrong. Erroneous, just wrong data. In this example here, We run through the program. So total equals 1, while the value is greater than 0. Well, sorry, we'll run down here on factorial 4. Yeah, factorial 4. So I hate these factorial problems. So we're going in with factorial 4. Total equals 1. Is the value greater than 0? It is. Well, total equals total times value. So that's going to be 4 times 1, and take 1 away from that. So first time around the loop, what I'm getting is a value of 3 and a total of 4. Okay, next time around the loop, value is still greater than 0. It is. So this time total is total times value. So that's going to end up being 12. And we take 1 away from the value. Still greater than 0. So we do it again. 2 times 12, 24. And value still 1. It's still greater than 0. So we do it again. 1 times 24 is 24. That's 0. It exits the procedure. Would you have to draw the table in the exam? This is the hard part about A2. A2, they don't give you an answer booklet. They just give you blank lined paper. It is an answer booklet, but it's just blank lined paper. You are going to be expected to plan out and design all of your answers. Okay. So keep an eye on those headings. Keep them in your head. You want to show which loop, the value and the total are the specific variables here. Okay. You need to read that and interpret it. If they're being nice to you, they might give you a table that starts and that you have to extend and complete. That's what I'd hope they do, but you never know. Now, everyone's favorite, I know my class love this. They can't get enough of it. They keep asking me for more and more Big O notation. Now, Big O notation generally is quite simple. If they give you some code and go, what is this? Becomes a bit harder. The idea is this: we cannot calculate and express the complexity of an algorithm in terms of the time that it takes to do something, okay? Because a computer running at different speeds would complete it in different times. What we can do is we can say how complex that algorithm is, okay? What we do, if we give it an expression, we're looking for the part of that expression that has the biggest impact upon how long it takes to complete. So first of all, whole number addition, subtraction are meaningless. Okay, 42 more instructions, great. I'm doing a 20 billion data set. And that's what n is, the amount of data in the data set. Okay, the multiplication of by 5, meaningless. Yeah, just to make it 5 times bigger. The thing that matters is that squared, n squared. It is getting massively bigger every time because it's being multiplied by n. That is the most significant factor. The rest of it's meaningless. So we'd say this expression has a big O of n squared. In the code, you need to look for recursion, iteration, and you need to look for the amount of times n is used within that data set, the amount of instructions that are used in a loop, because that will help you calculate it. Go and look at the past paper questions for this topic, because there is some weird stuff that they're asking you about. They'll give you loops and they'll ask you directly, what is the big O of this loop? If you see any loop within a loop, there's probably n squared, but you probably need to look to see if there's anything else going on. If there's another loop after it, it's probably n squared plus n. There's a bunch of things you need to look for. Go and watch my video on the past paper questions for this one, please, because this is the one that could kick you in the teeth. Quick question. Can this be the same for different exam boards? It changes a lot. I'm not sure it's exactly the same for OCR, but the basic knowledge is the same. I'm going to make no comment about this one, but occasionally we do get a mark scheme where it's hard to work out where the answer's coming from. A lot of the problem is, of course, they do write exam papers with a specific answer in mind. But that's why they have moderation meetings. Okay, so after your exam, they'll have a meeting with all the examiners to discuss the questions and to make it a bit fairer on you. Okay, big O, fastest to slowest. Let's start. Constant. This is where it takes the same amount of time to do anything. That would be big O, 1. A push or pop on a stack is an example of this. Logarithmic. Now, in a logarithm, it's like the inverse of an exponential. It increases, but the amount it increases by gets less each time we go up in the value of n. So it's increasing, but it sort of tapers off as we go. Binary search is an example of that. Okay, getting worse as we go. Linear just means it scales with the amount of things in the data set. If we've got 10 billion things in the data set, it's going to take me 10 billion goes. If I've got 20 billion, it's going to take me 20 billion. So linear, and we could have multiplications of that. We could have like 3n, but we never put the numerical multiplier on there. Things like that are things like simple search, where we're just going one after another through the data set. It's always going to be take the same amount of time as the data set. Okay. The other logarithmic, with WJEC very helpfully called logarithmic, which doesn't help very much when you've got another logarithmic. This is n log n. So it's a multiplication of it's going up by n, so it's a normal linear one, but there's a little bit extra each time, but the little bit extra drops off. So it's basically as if you'd added the last two together. It's slightly worse than linear, but not that bad. Example of that would be quicksort. Polynomial. This is bad. This is n squared, n cubed, anything like that, where we've got n is the amount of things in the data set, and c is a number. You don't need to compute c at all, but c is just a fixed number. We basically are going up massively each time, aren't we? It's n times n 3 times. Okay, selection sort's an example of that. Bad now, exponential. Okay, c to the n. So it's a numerical value to the power of the data set. That means that the problem is almost impossible to solve in any reasonable amount of time. The traveling salesman problem is the only real example of that you need to worry about, because there are very few others. Most people say to me, why do I need exponential? Surely I'm always looking to make my big O as far to the left as possible. And you're right. In most processes, you want the quickest that you can do. But in things like encryption, you don't want people to be able to break into your password quickly. So with encryption, you want exponential big O for trying to break out the problem. A few people asking me what the traveling salesman problem is. I don't really have time to go into it tonight, and it's not part of your spec in so much as you don't need to really know what it is, but it's the only good example of this. It is where you have a situation where a salesman needs to go and visit a number of locations around the country, and we need to work out the most efficient way of doing that. There is no easy way to plan that route out other than manually working out each individual route and seeing which is the smallest. So, great. There's a bunch of good computer file videos on that. If you want to do a bit of a Google after I finish tonight, there's a bunch of good stuff on there. So don't panic. If you don't know what it is, it's not desperate. Here's a few examples in terms of like data set size. If we set n as 20 here, so there are 20 things in the data set, a constant would just be a fixed amount of time. So we've just said 3 for that. Logarithmic, it would be 1.3. Linear is the size of the data set, so it's n, it's 20. Logarithmic, 26. You'll see it's only a slight rise. And then you'll see why it gets bad. Polynomial's gone to 400. Exponential is what? 1.04 million. So the amount of comparisons or whatever you want to do goes up drastically. If we look at them all, you'll see how they overlap and how they're problematic. Big O notation, they love asking about it. Okay, shortest path algorithm. Go and grab my video on 4.2 data transmission to have a better look at this. But in Unit 3, they tend to ask very simple versions of this, where what you have to do is work out the cost from the starting node to each of the other nodes and the shortest route to get to it. And you can usually do this quite manually. So for instance, in this table, I'm saying that going from A to C, the easiest way is to go directly, which is a cost of 2. To go from A to D, the quickest way is to go through B, which is an overall cost of 5. Okay, Dijkstra's algorithm. You should theoretically need to know the details of Dijkstra's algorithm. They may ask you a question, but they never have. They never have. I taught OCR for a number of years, and OCR would give you a Dijkstra's question every single year. And it was a very high marking question. It was, 15 to 20 marks. It was almost like a grade and a half for this one question. With that in mind, then, do I think it's fair that they might ask you a Dijkstra's question this year? Probably not. This wouldn't be the year that I would introduce it, but I'm not the WJEC. They may do something a little bit different. They may stick it in. You should need to know it. Now, the idea of Dijkstra's is very simple. You start at the beginning and you, quick question, sorry. Now, yeah, they can't do it for the first time in a year like now, can they? They shouldn't, but they can do anything they want. The specification is there. They've made their accommodations. If they want to ask you about Dijkstra's this year, they will. Whether the marks would be very high as a result, I would doubt that very much. They've never asked a question about it in any of the previous exams. Very quickly, Dijkstra. From where we are, we identify all the vertices to the nodes that I can get to, and we put them in order of size. So from A, I can go to C and B. C is the shortest path, so I'd look at that next. Once I've visited, we'd mark it off as complete. C, I'm going to go to next. So from C, I can go to B and D. B, you'll notice change then, because going to B from C was actually shorter. So that updated that one. And D was a value of 6. C is done. I move on to B. If I'm looking at B then, I can go to D and E. D is 5, best from B still, and E is 8, best from B. Okay, from D, I can basically just go to E, and the best way to go there is from D. And then if I work out E, there's nowhere to go, and I've completed my node map. The only problem with Dijkstra's algorithm is if you've got one long road and a series of shorter roads, it's going to prioritize the shorter roads. So it's not the best way of doing something weird. Sorry, I've missed this bit, but if you're going to explain that, what you need to do then is follow the road back from the destination. So you'd say, okay, this is best done in 6. The way you do it is you do DE, which is that one there. And the next one you do D. So that's going to be BD, which is that one there. And you go to B and you say, all right, that is CB, which is that one there. You go to C and that is AC. And as soon as you hit the starting node, it goes in there. Again, we've never seen a question like this. There are OCR example questions about this if you want something. If you Google OCR A-level computer science Dijkstra, you'll find some example questions where they actually work through it. But there aren't any for the WJEC. A star is a much better version of this because instead of just using the distance, we use a heuristic. This is a rough idea of how far it is away. I haven't got an example of this to take you through it, but basically you'd say, right, A to E from B is roughly about 7. This is, if it's going in the right direction, you give it a bigger number. If it's going in the wrong direction, you give it a lower number. And what you do is you multiply the distance by the heuristic in order to work out which would be higher on the list. That means if we're going in the right direction, it would prioritize those heuristics. Then a quick reminder of the basic search and sort algorithms you need to know. Linear search works on an unordered list. It is big O N. If I'm looking for D, I go like this. Is it here? No. Is it here? No. Is it here? Boom, done. Work from left to right. The reason it's big O to the N is because I might have to search through everything. Binary search is logarithmic. Now, what we're going to do with binary search, because it only works on an ordered list, is we say, okay, I'm looking for D. Find the midpoint. Is that D? No. But I know that D is greater than C, so I can ignore the left-hand side. What's left? Find the midpoint. Boom. D, that's not D, but D is to the left of it. Last thing that's left is this D. 3 steps. No matter how big that data set is, I can get through it in a much shorter amount of time. Okay. Searching, you need to be able to read, write, edit, and discuss these algorithms written as pseudocode. So please do go and check the past paper questions because that is what they're going to be asking you. Different sorting algorithms have different characteristics. We need both iterative and recursive algorithms as they have different characteristics. And you might need to talk about the efficiency of algorithms as well. Now, the way you talk about the efficiency of an algorithm is quite simple. You go through how much storage space is needed. Obviously, less is better. You go through the number of comparisons you need. Less is better. You go through the number of exchanges you need. Less is better. You also do the number of passes you need. Less is better. Sorts, I'll be coming on to those in a minute, hopefully, as long as I haven't accidentally deleted the wrong Here we go. So bubble sort, first of all. Now bubble sort worked this way. Now there's two types of comparison here: time complexity and space complexity. So space complexity is how much memory do I need? Time complexity is how long it's going to take. Bubble sort's the worst. I need the same amount of memory, but it's a polynomial amount of time. And the reason for that is I need to go through in pairs and decide if any of those pairs need to be swapped. So A's before C have made a swap. The moment you've made a swap, you need to go all the way through the list again next time. C and D look right, D and E look right, E and F look right, F and B wrong way around. So because I've made at least one swap, I'd go back and do it again. Fast forwarding, eventually I get to the right thing, but I have to keep going until I've gone from left to right without swapping anything. Bad time. Insertion sort. Time complexity, polynomial again, bad. Space complexity, constant, good. Insertion sort works like this. Okay, I'll take the first element out. It's on its own. It's a sorted list. I take the next element. I put it in the right place. I take the next element. I put it in the right place. I take the next element and put it in the right place. If you're looking at this and thinking, how do you put it in the right place? Well, as far as WJ is concerned, it's a linear search. This is a terrible implementation of an insertion sort. Okay, it looks quick when I demo it like that. It looks quick the way they asked me to explain it to you, but it is not. An insertion sort, we need to decide how to insert it. That's part of the skill. And because of that, it is not a good type of sort. Merge sort. This is my favorite. It's logarithmic, n log n, logarithmic. So it's slightly worse than n, but not that much worse. It's got linear space complexity as well. We don't need any more space. The way it works is like this. We split everything up into individual elements. We pair them up. We put the pairs in the right order because there's only two things. We do that by comparing the first element in each set. Okay, C and A, which comes first? A, then C. Boom, sorted. We do that with E and F. Boom, do it with D and B. Boom. We then pair up the pairs. Now I've got an odd number, so I'll just do these two first. Now, we are comparing the leftmost item in each of the sets. So A versus E, which one comes down first? It's going to be A. Okay, then we're comparing the first item in each of the sets. C versus E. Well, it's C. Then E, then F. See that? We're always comparing the leftmost thing. Again, people are asking me, do we need to know the pseudocode for it? You could be asked to edit, write, or understand the pseudocode for any of these things. I would think it'd be a bit mean this year if they just went, write a merge sort algorithm. Difficult. So we go from there then, and we're saying, right, which one comes down first? A or B? It's A. Then A or C? It's B. Sorry, A or B. Then C or D. Then E or D. Then E. Then F. Boom. Whoosh. Doof. Merge sort. Yeah. Yes, it is in the specification. All of these are in the AS specification, and they could ask you about any of them. So it's worth knowing about all of them. Okay. So they do sometimes bring things up from AS into the A2, which is why I've got that there. So just be careful with that, because again, hopefully it won't be a problem this year, but they could. Right, quick. So if you want any of this stuff, please do have a look at my videos. I think I've got some pseudocode for most of these in my videos. Quick sort. Logarithmic in time. Good. Logarithmic in space as well. So that means we're using less than the amount of data we need. Quick sort. Beautiful thing. Watch this, because it is quick, right? We take the first element down. That's a sorted set. We take A down. We pop it over there. We put F down to the right-hand side, because what we've done, that yellow element is our pivot point. And every item that's coming down is either going to the left or the right. E's going to come down now. Now, E's going to go to the right, but notice that's not in the right order. I've just brought it down. I'm not sorting these things out. I'm just bringing them down and chucking them in. Once we've done that once, the pivot point is locked. That is in the right place. That is sorted and locked. So we need to do the same thing with these two other subsets. So with this one on the left, I'm going to take A to be the pivot point. B goes in to the right. A is locked, C is locked. Over here, take F to be the pivot point. E goes in this side, D goes in this side. F is locked. Anything size 1 is already sorted, lock it down there. E and D, take down the first item, lock it, pivot point. D goes in there. E is sorted. D is a single set, boosh, done. Dusted, happy. Okay, is that one done? The one they like to talk about is quick sort and bubble sort. They love bubble sort. They love bubble sort so much, like it's another child. So please do make sure you are aware of bubble sort. Do make sure you're aware of quick sort and all this stuff. Okay. I see a bit of discussion about whether it is in the specification. Let's have a look. What's this one saying? You might be right. I've done these slides quite a while ago. It might have changed, but I think it is in there somewhere. It might be in one of the other units. But anyway, don't panic about it. All right. Merge sort, very, very easy. But quick sort, pivot points, boom, boom, boom. Happy days. We've gone past the hour. The rest of it's short. I'll try and be done in 15 minutes. You can catch up on Love Island. Principles of programming. Very, very simple. Key thing here. Validation and verification. Just a reminder. Validation. Can we make sure it makes sense? Verification. Is it actually written down and is it correct? The red ones, the verification, is very, very difficult because it's very hard to check whether something is correct. You ask somebody their name, how do you check it's correct unless you go and validate all their stuff? Don't worry, guys, I'm not going to rush. I'll take my time, but I'll try and be done as quick as I can. Validation's easier. Validation is basically, does this look right? And that's a lot easier to do because we can do things like lookup checks. Is it part of a list? Type checks. Is it an integer if I've asked for a whole number value? I'm going to take a range check just to show you some examples because, again, this is the sort of thing they could ask you to write in pseudocode or they could ask you to understand from pseudocode. Now, a range check is between two values. Here's an example. We're inputting a value. We're saying if it's less than 0 or greater than 18, we'll error. We'll ask them to type it in again. That is a simple example of a range check in pseudo that makes sure that somebody is greater than 0 but less than 18. I don't know why you need that validation, but it could be a straightforward thing to ask. Logical operations, okay, manipulating conditions. Again, we've got our not, so it gives you the opposite. We've got and, both values must be true. And the way we write that in code is we write variable and another variable. With a not, we just write not before it. Well, we do that in Python. In most of the programming language, you put an exclamation mark in front of it. Or is literally just the word or. Either or both can be true to get the true value out of it. XOR. Now, XOR is difficult to write in Python. Most of the time in pseudocode, you write if this value XOR that value. To write it, you have to put a bunch of nots in. It gets quite complicated. But basically, XOR, only one of the values must be true, not both of them. And that's the big difference there. And then the two that you need to care about from this year, a NAND gate, not and. We just write NAND in the middle of it. And then finally, nor, not or. Both the values must be false for it to work. It can just be a not to an or, and an and can be a not to an and in brackets. The logical operations being used in pseudo are less likely to happen, but it can happen. So we try to avoid that. You also need to be able to read and write algorithms that allow you to move through different data structures. Okay. I'm not going over the same thing here. I'm talking to you about how you'd write it in pseudo. So please be aware. There's a difference between understanding what the structure means and being able to apply it in this part of the specification. This part of the specification is much more about, can you read, write, and interpret pseudocode for these things? Okay, this one, traversal. Moving through a data structure, you need to be able to traverse all those things in both pseudo and or code and understand it and write it. Have a look at the data structures unit. Again, in the slides that I've given you and the videos that are already there if you want more about that. But as a quick example, here's how I traverse a one-dimensional array. And what we're saying here is we've got a loop that's going one at a time through them. So when you traverse a one-dimensional array, you go through the individual rows. When you traverse a 2D array, it works a little bit differently. You go through a row at a time, but column by column. So we're going left to right for each column as you traverse a 2D array. And that's important to remember. This is what's happening where you've got the for loop within the for loop. It's going from left to right, a row at a time. This is why you probably won't get a 3D array question. It is not the code itself to loop through it, which is reasonably straightforward. It's a for loop in a for loop in a for loop. But it is writing the array as code. That is just two different tables in a three-dimensional array here. I'll pop back and do some and ors in a second for those of you that are a little bit confused with that one. But do go and just have a look at those videos. The only reason you need to know them, the and or at this point in code, is if they're in an if statement. If this and this, that's what we're talking about here, having two parts in it. Presence check is where an item has to exist within an array. It's often one that you don't get marks for, so I'd avoid that, but it is a valid type of check. So 3D arrays, very difficult to express them, but the way in which you traverse them is you start at 0, 0 on the first table, and you do normal 2D array traversal. And once you finish that array, what happens is you go boop to the next table and do it left to right again as you go through it. Okay, data compression. Data compression is where we reduce the amount of space that a file takes up. That could be in memory, that could be in RAM, that could be in secondary storage. We trade off the time, the storage space with processing requirements. And there are two main types. Lossless. That's where we reduce the file with mathematics. And we have to uncompress it to get it back, but we can get it back in the original condition. Lossy, like an MP3 file, is where we reduce the size by throwing bits away. You can never get back to the original file. But if you can't tell the difference, there's an argument that says, does that really matter? It does in some cases, and it certainly does with photographs. If you take a photograph that's stored in a lossy format and you try and change the brightness, there is unfortunately not going to be a lot you can do. All you're really doing is making the dark colors lighter gray. In a lossless picture, you'd have the actual color value of every pixel, so you'd be able to see what was in those shadows. How do you compare compression? Well, the first thing is the compression ratio. It's the size of the compressed file divided by the original file. You've also got the time it takes to compress that file. The longer, the worse it is, clearly. Then you've got the decompression time. How long is it going to take you to turn it back into a readable file? The greater that is, the worse it is for a compression algorithm. Also, what percentage you're saving. The bigger the percentage you're saving, the better. All four of those are the steps you'd go through to talk about and compare a compression. I'll give you an example to that one here. If I had a scenario that was talking about a compression ratio, which is remember the size of the compressed file divided by the original file. So we maybe get I don't know, 100 kilobyte file out of a megabyte file. Then we are basically got it's reduced to 10% of the original file. Compression time, if that is huge, that's problematic. But actually having a big compression time and a small decompression time is ideal if that file is then used or read a lot more than it is compressed. So like music is like this. It is better to take more time to compress music or a video file so that it's quicker to decompress so that you can have it read and watched in a quicker way. You need to be cognizant of all these four facts because in a scenario, you need to balance all four of them. Okay. Programming. This is where we talk in a bit detail about paradigms, which are one of my favorite things. Paradigms are styles of programming. There are loads of past paper questions about this. Paradigms have purposes and uses. The most obvious one is procedural languages. This is normally what we use. It's step-by-step code. Non-procedural languages tell us what we want it to do without explaining how to do it. Things like Swift UI are non-procedural. They're declarative. You say, I would like a button that looks like this, and it decides how to do it in the most appropriate way. Scripting languages are procedural, interpreted, and allow embedding of code in other projects. So this is things like JavaScript or Python in most cases. OOP, object-orientated, uses objects, classes, and encapsulation, inheritance, and polymorphism. In other words, they're good for games. They're good where I'm creating a template of something and I'm using it lots. Special purpose languages, like things for machine learning or expert systems, are good for that specific purpose, but not much else. We are on currently 4th generation languages, which is how far we are away from the machine code, which is what runs the computer. Natural languages are where we would speak in a very natural way, and we need to infer the understanding from that. So that's more like turning English into code. Visual programming using blocks like Scratch. And application programming packages can also have programming capabilities. These are things like Excel, which have a programming language built into them so you can extend them. Again, all these things you sort of need to be able to talk about. Object-oriented programming is the one they love. You have classes, and you can think of a class as a template. When you instantiate or create an instance of a class, you end up with an object. And that's a real version of it. That's something that actually exists in the program then. Methods are actions that can be performed on the object. They are the code. And properties are the data. This is how you draw an OOP diagram. You have the name of the class at the top. You have the properties, and that's the data that it stores about itself, and the methods, the code, the functions that it has about itself. One of the nice things you can do with OOP is you can use inheritance. Both these two classes, NPC and player, inherit from character. Now, NPC has location and dialogue. It has methods and code that run within it. Player has the same thing. It has controls and health and code that runs within it. But because they both inherit from character, they both get all the character had as well. So both an NPC and a player have a name and a model. Both an NPC and a player have set name, get name, set model. And by doing this, we can actually reduce the amount of work we have to do to express something within the game. In programming as well, we need to care about standardization. Standardization means keeping things similar. And the reason for that is programs should be portable. You should be able to take them to most places. Programmers need to be portable as well. It would be a great place to be able to move from one software engineering program to another. You also want your software to be reasonably easy to maintain. Acceptability, is it good enough? Does it do the job? Can we check that? We also want faster development. And if things are standardized, if things are similar, you're going to get better development quicker. We might use a standard library of things so we can all pick from the same graphics. And that's what games have sort of become in recent years. Things like the Unreal Engine are sort of like a standard library. So things tend to look the same. And finally, standard algorithms. Standard algorithms are things like binary search. They are things like quicksort. Standard algorithms are important because we know how long they're going to take. Well, we know the big O of how long, or the space, or the time complexity requirements, so we can plan for them. And if everyone understands an algorithm because it's standard, you'll probably be able to implement it well. There are loads of issues with complicated algorithms, especially in cryptography and on the CPU, where you have problems that are always there, but people find them 20 years in the future, and they've been there for a long time because people don't understand them. Standard algorithms are better because everyone understands them, and if you understand them, you can stop them breaking. The problem with standards, though, is everyone needs to buy into it. In the 90s, it was a nightmare in the web because Internet Explorer was the #1 web browser and was doing its own thing. So it was really hard to write a website that would work on anything other than Internet Explorer. Apple have been in the news lately for its Lightning port. You know, the EU are going to standardize on USB-C, and that might not be great for Apple and might not be great for everybody else. But because we want standards, you do need to actually produce them. USB-C by itself, right, is the same technically as Thunderbolt. USB 4, I believe, is the same as Thunderbolt 4. There's some overlap there, or I can't even remember what it is. It's so complicated, but they use the same cable. Have you tried buying cables for Thunderbolt devices? Because they look like USB cables. Standardization is difficult, but it is important. Natural language has ambiguity, okay? If I say, set an alarm for 5, right? What do I mean? Do I mean 5 p.m.? Do I mean 5 a.m.? Siri, for some reason, always picks a.m. for me. Cheers, Siri. I don't want an alarm for 5 a.m. in the morning if I want something reminded in a few minutes. One day it'll get it right, but because natural language has ambiguities, we as people often have to ask for clarification. Because we have to ask for clarification, it means that computers can't just understand what you mean in the first go. In mathematics, we use things like BIDMAS for removing ambiguity. Programming languages cannot have ambiguity. Because of that, we need to explain the syntax of a program in a couple of ways. These questions I honestly think are reasonably straightforward. But there are two ways to define the syntax of a program: a syntax diagram. You can unambiguously define the syntax of a program in this way. In this example, a variable name would have a letter followed by any number of numbers followed by a dollar symbol. These symbols are taken straight out of flow diagrams as a subroutine, so you'd expect also to see a diagram for a letter that explains what a letter would be or what a number would be. You can usually assume that letter or number have already been done for you. Syntax diagrams, if you're reading them, are easy. If you're writing them, just have a little think about whether we need to have one or possibly none of an object, because you're going to have arrows going in different places. Go have a look at the past paper questions on this one, please. Because that example assumed I'd already defined letters and numbers previously, and those bits of the diagram get quite big. BNF, Backus Now Form, is how we define that in a written way. Now, this is often where people start scratching their heads. You have to define an object. So in this case, on the first line, I've defined a letter. That syntax is important. A letter is going to be A or B or C or D or E or F. A digit is going to be 0 or 1 or 2 or 3, blah, blah, blah. Then a number can be a digit or a digit followed by a number. Notice we've got recursion built into this. And this is why these questions become quite difficult. Because a variable then is going to be a letter followed by a number followed by a dollar. And a number could be one number, or it could be a number followed by another number followed by another number. And this recursive element here means that I can have much more of that. The dollar sign is an arbitrary value that I've put in or I've taken from a past paper question. The dollar sign is not syntactically important. It is just a symbol that was in this particular question from that year. Okay, Backus Now Form. Go look at the past paper questions on that one, because that one is a pain. Okay, and that last bit, sorry, was quite lengthy. Systems analysis. You were supposed to know for AS level the waterfall model. No one uses the waterfall model in the real world. My God, honestly, where you have to do everything in order. This is what you did for your NEA, for your coursework. You did a feasibility study, then you did analysis, then you designed it, then you implemented, then you tested it. Well, great. The problem is, if any of the stages you have to stop and go back, you have to go back and work your way through them all again. This is the sort of system where you spend 2 years designing something and then 2 years building it. If there's anything wrong with the design, you have to go back and start again. It is a nightmare. The only good thing about it is it's easy to plan out and clients know what to expect and when. If there are bugs, you're knackered. If there's problems, you're knackered. If a client says, actually, I want this on mobile, you're knackered. You have to go back to the start and work your way through every stage again. Waterfall, nightmare. The better model is agile. Agile is an iterative process. The idea with agile is we take a bunch of those things that were in the waterfall model and we start working on a simple design. And once the simple design is done, we test it and we evaluate it. And then we take anything that we've learned from that to iterate and improve it on the next cycle. So the idea of agile is that we start with a small thing, and once that's going, we improve it and we extend it. And if there's ever any problem, if there's ever a problem, any small bit of it, we notice it as we go and we fix it. As part of agile, there's a bunch of other things that are in it, like sprints, where you just code constantly for a couple of weeks and you ignore everything else. Scrum, where you get together in the morning to have a chat about what you're doing. Peer programming, where you work together. One of you is the navigator telling the other what to do, and the other one's the driver. There's a bunch of stuff. Go and have a quick look up at it. Agile is brilliant. Because testing is going on all the time, because the customer's involved, if you haven't got a clear goal, this is good for you. If you're a small team, this is good for you. But there are no real plans in advance. So because that clarity is poor, because the time scale is poor, it can be hard to develop that fully. It can be hard to tell a company, this is going to take us 2 years and cost this amount of money, because we don't really know what we're dealing with there. Documentation that you'll need then, you'll need a requirement specification, design. I mean, all this stuff you've done in your NEA. So this should be something simple on the top of your head there. But key is there needs to be technical and user documentation. So technical documentation about what you've built and user documentation about how to use it. That's where those bits of documentation fit into the plan. Okay. Technical and user documentation is in the implementation, testing, and installation phase. Everything else is in analysis and design. Very often they'll ask you questions about this that want you to waffle about it for ages. They're a little boring. This is chapter 7. Sorry, didn't give it a heading or a title card. Software engineering tools, things like an IDE, an integrated development environment, make software easier to use. How? Well, things like autocomplete. Start typing, it suggests code or it suggests variables. Bracket matching. Click on a bracket, it shows you its matching pair. It is absolutely brilliant for making sure that your code is working correctly. Syntax check. It uses a little red squiggly line just like Word does to tell me if my syntax is wrong. Better than clicking run and trying to find out where that problem is. Syntax highlighting is where it changes the color of different parts of the syntax so it's easier to read. None of this you get in a bog standard IDE. Right, testing. There's a couple of ways of running a debugger in an IDE that we don't really use that much at this level. Stepping is where we go through the code one line at a time and see what's happening to the variables. And variable watch allows you to show and display how a variable changes as the program executes. Breakpoints allow me to click on a line of code. In this example, I've put a breakpoint on line 3. It'll run the program as normal and pause at that breakpoint to show me what the variables look like. That way, I can put a stop anywhere where I think there might be a problem to examine what's happening. There are also some tools associated with this, case tools, and because we're computer science nerds, they've got comedy names. Uppercase tools are tools to deal with planning, analysis, and design, and lowercase tools are about implementation, testing, and maintenance. Analysis tools allow you to help you fact find. These are things that help you coordinate the investigations, the meetings, the questionnaires, getting all that information together. You're pulling that back in and keeping it all in a system. Diagrams, I'm sure many of you have used electronic diagramming tools. You don't really want to be drawing things like entity relationship diagrams manually, because if you need to move things around, you're getting your eraser out and getting rid of loads of different things. With this example here, I'm making an entity relationship diagram. I can move things around. I can change the connectors and it can make it look nice for me. It's a much easier way of doing that. I'm not going to be putting up a link to this PowerPoint. I'm sorry, because there's just too much to it. But all of this PowerPoint is it is the videos that are up on my YouTube channel already, where I explain each of the topics. So if you go into the first video for each of the topics, you're getting this same presentation in a bit more detail. Project planning tools allow you to create things like Gantt charts. If you've done business, you'll be familiar with these, but just ways of planning out the project. Whose responsibility is it? When do you need to get things done? What happens if they're late? Stuff like that. Collaboration tools allow you to share resources. A good example of this is a design tool called Figma, which is where you can plan out the user experience and the design of the user interface and share it with people and comment on it and things like that. It's really, really useful if you're building software together. Automated testing is a great way of writing tests, so you're not having to manually test everything. Then if you change one thing, the automated tests can check that you haven't broken anything. Bug tracking software to keep an eye on the bugs you're having and things like that, so you can track them and you can check when they've been fixed or if they haven't. And then test planning software that'll help you plan those tests out. Well, hey, one of the key bits of software, though, that you've probably not used much is version management software. Things like Git. GitHub and Git are technologies that allow you to keep copies of versions of your software as you change them. And it's every change. You would check in and check out a file, and so everyone knows you're working on them. And if you've made a mistake, if you've broken something, you can go back to any old version for any file in your software. This is an example of my GitHub page for a piece of software that I was working on. And you can see there that every time I make a commit, I make some comments about what I've done, and it shows me files I've modified, files I've added, and I can actually go into them and I can see what's changed on each particular line of code. So I can see the tiny changes that I'm making. Last one, and this is the shortest one. Despite the fact that in AS, this topic is huge. This topic was removed from your AS specification, okay? However, there is an element of any question they ask you could theoretically contain content from the AS stuff. I think it would be mean if they did. All I'm going to talk about tonight is what is in the A2, because this is the only thing in the A2. Professional behavior. Well, what does that mean? Being a professional, being a computer science professional in particular, means we adhere to a series of rules to make sure that your customers have confidence in you. That involves agreeing to a code of conduct, which is things that I will do as a working professional and things that I won't. You probably signed up to one of these when you started at your school or when you took for the first time, you logged into your computers. The problem is they like asking questions about what's in a code of conduct. And there's nothing more boring than explaining what's going to be in a code of conduct. At the very simple level, it's the steps and the professional standards required to get in. It includes standards for professional competence. In other words, I will not say that I can do something that I can't. And integrity, making sure I follow through on things. Things like, I should not claim a competence in something I don't possess. I should not be saying, oh yeah, I understand Rust perfectly if I've never seen it before. It's about being honest. Keeping their suite of skills up to date with regular CPD, continuous professional development. I'm not just going to be working in Fortran my entire life, so it's good to improve and update your skills. Promoting equality and inclusion and not discriminating, again, is very, very important as a developer in the software industry. You want to make sure you have knowledge of the relevant laws and legislation, because if you are doing something that is illegal, it is the clients and you that will be in hot water at the end of it. Developers should seek and respect critique. You should ask for people to feedback on your code, and you should enjoy that process and be happy about it. You should work without injuring others, including property or reputation. You can't be rage quitting your job and throwing a laptop at a wall. It's important as a developer, as a professional, to make sure that you maintain standards. And that's what these code of conduct questions can be about. Now, if we get a code of conduct question, I hope it's a short one, because if it's a long one, they're massively boring. rejecting bribery or other unethical inducement to work. All right, fair enough. Respect the confidentiality of the clients. Great. Keep their secrets secrets. And then this one, which I'm sure applies to lots of you, you should not use pirated or illegal software if you're being paid to develop software, because that sort of defeats the purpose. Individual organizations may have code of conducts that talk about the levels of privacy or disclosure they're willing to go to, the levels of access to resources and materials, who's allowed access to what, and what sort of skill level should they have, who owns the intellectual property. If you've been working on software for 4 years and you leave the company, is it yours or is it the company's? And then conduct of individuals on social media. This is really important. Making sure that you haven't got people trolling other people on social media, which is traceable back to the company. That's it. The topic list is done. 1 hour, 31 minutes. Oh, dear me. I'm very sorry that I broke into your Love Island watching time. I've seen a few questions jumping up about other ethical stuff about GDPR and stuff like that. Look, the AS content, right? The AS content is theoretically something they could ask you about. For your AS level qualification, that was removed from your topic list. I don't know, though, if they understand that. I don't know if they care. They may ask you about GDPR and the Computer Misuse Act and things that you probably now haven't seen since GCSE, or things that you might have covered quickly last year. We have to be careful, and we have to just make sure that we've done a quick bit of a review of those things. But go and have a look at the past paper questions. If we keep our fingers crossed and they play nice with us, most of the paper will be past paper question style. Let's keep our fingers crossed, eh? Right, I'll be finishing up in a few minutes, so if you've got any actual questions about the paper, please do. Now, once again, I am not able to see the paper until I think the end of tomorrow at the earliest, probably the day after. So I can't really give you any feedback until then. But my class specifically, do come see me tomorrow. Let me know how you got on. Let me know what questions were good, what were bad, what were horrible, and try your very best. As I said earlier, if they're anything like the GCSE and the AS level exam papers, they're going to seem really weird because some of the questions are written in a strange way. And I think it's just 2 or 3 years of them iterating on exam papers without us seeing what they're producing, or they're trying to be nice to us. And because they're trying to be nice to us, they're trying to simplify the questions, and they're trying their best to help us out. They are. They've got our best interests at heart. But you will be seeing these questions for the first time. So do your very best. This, I personally think, Unit 3 is the bigger of the 2 units in terms of quantity of stuff they could ask you. Unit 4 will be much more straightforward, although the exceptions they've made for Unit 4 are a bit weirder. Revise, have a good night's sleep, because that is really important, and I will see you in the morning, and you will smash the exam. Good luck to everyone, and I hope that you have a cracking exam tomorrow and you absolutely smash it.